as we had said in the last lecture, today we are going to talk about certain basic facts about convex optimization itself. That is, we are going to discuss today the minimization of a convex function f subject to x belonging to a convex set C. So, this is what I called a convex function and this is what I call a convex set. Now, of course, the question is what is a convex function and what is a convex set. Now, before I start the full fledged discussion, let me tell you that I would like to show you a book which I think everybody should have a look at it. This book is called Optimization Insights and Application, written by Jan Brinquist and Vladimir Tikhomirov, and I have spoken about a book called Stories About Maxima and Minima, written by Vladimir Tikhomirov. This book is a fabulous book, whether you want to do convex optimization or even the non-convex one, has a huge amount of insight. It is published by Princeton University Press in the Princeton series in applied mathematics, quite a recent publication, and it is just a mind blowing read, and in fact, it is something everybody who wants to do anything with optimization should have a copy in their desk. So, going back, we will first define what is a convex set. Simply put, convex set means that if I take a set in generally in Rn, but as always we will look into the pictures in R2 and take 2 points x and y in this set, any 2 points, and join them by a line segment, then this line segment should also remain inside the set. Now, if you look at this set, whatever points you take and whenever you join them, they remain inside this set. You take a set like this, I take a point here, I take a point here, and I try to join it, it goes outside, or a set like this, it is more clear. If I take these 2 points, I join them, a part of the line segment is outside the set. So, this set is convex, these two are non-convex. If you look at your own body, your human body, the human body is non-convex, because if you take a point here, I take a point here, you join them, it is completely outside the body. So, human body is a non-convex thing, is a non-convex set. Now, how do I formalize this definition, that if I join any pair of points by a line segment, the line segment has to be in the set, and that sort of set is called a convex set. So, to begin with, I will talk about the given any 2 points x and y in Rn, the definition of a line segment. The line segment is usually denoted as with this symbol. It is a set of all z which is expressed as lambda times y into 1 minus lambda times x, where lambda is a number between 0 and 1. So, it means if I take these 2 points x and y, and if I put lambda equal to 0 here, I am getting x, and if I put lambda equal to 1, I am getting y. So, as I vary lambda from 0 to 1, we move along this line from x to y. So, it is clear that this is nothing but the simple geometric line segment that we know. So, even when you are talking about 2 points in 3 dimensional space, we are talking about this line segment. Now, formally, a convex set is a set such that for any x y in the set x y line segment is also a subset of the set. So, this is just a thing in the English language which you now understand very well. Now, what is a convex function? A convex function can be defined from Rn to R, or it can be defined from a convex subset C to R, where C is a subset of Rn and is convex. Now, the most original or the most, or rather I would say the earliest definition of a convex function was due to Jensen, W.B.B. Jensen. And Jensen gave this definition which says that if you consider from Rn to R or even from C to R. So, f of lambda y plus 1 minus lambda x. See, this is very well defined. If you take a convex set C and y and x two elements of C, then lambda y plus 1 minus lambda x, whenever lambda is between 0 and 1 is element of C. So, this functional operation is well defined. This has to be less than lambda times f y plus 1 minus lambda times f x for all x y in Rn or C and lambda in 0 1. This is the definition of Jensen, but a much more modern definition can be given in terms of epigraph. Epigraph of a function f is everything that lies above the graph. So, if this is a function f and this is the graph, then epigraph is the dotted portion along with the outer curve. Anything above the graph is called the epigraph. So, this is the epf, epigraph of f. Okay. So, the epigraph of f, which we denote as epf, is the collection of all elements x alpha, where x is in Rn and alpha is in R, such that f of x must be less than or equal to alpha, which is very clear from the diagram. Now, what you can prove is that a function is convex if and only if its epigraph is convex. Now, proving this is a simple fact, because you look at this function whose epigraph is convex, then you can prove that this definition satisfies the definition that we had given on this page. So, going ahead, let me try to prove that if f is convex, then epigraph of f is convex. So, let us assume that f is convex. Now, you consider two elements x 1 alpha 1 and x 2 alpha 2 from the epigraph of f, both of them. Now, if you make a combination lambda x 1 alpha 1 plus 1 minus lambda x 2 alpha 2, where lambda is some number between 0 and 1, then this just means lambda x 1 plus 1 minus lambda of x 2 comma lambda times alpha 1 plus 1 minus lambda times alpha 2. So, I have said that epigraph of f is convex, right. Now, since f is convex, I have to prove that the epigraph of f is convex. Now, convexity of f tells me that lambda x 1 plus 1 minus lambda x 2 is less than lambda f of x 1 plus 1 minus lambda f of x 2. You must remember one thing, if your lambda is attached here, your f x 1 lambda gets attached to f x 1. If 1 minus lambda is with x 2, 1 minus lambda on this side gets attached to f x 2. But since x 1 alpha 1 is in the epigraph, f of x 1 is less than alpha 1, and since x 2 and alpha 2 is in the epigraph, f x 2 is less than alpha 2. So, which means that f of this would imply that f of lambda x 1 plus 1 minus lambda x 2 is less than equal to lambda alpha 1 plus 1 minus lambda alpha 2. By the very definition of the epigraph, go back once again, check the definition, look at this definition, f x is less than equal to alpha, all such x alphas for which this occurs. So, this is an x and this is an alpha, this is in R n and this is in R, and then this would imply that lambda x 1 plus 1 minus lambda x 2, lambda alpha 1 plus 1 minus lambda alpha 2, this is in the epigraph. So, I have taken two arbitrary elements in the from the epigraph and showed that their convex combination lies in the epigraph, which proves that APF is convex or is a convex set, to be more precise. Now, suppose I want to go back, I want to go back and prove that given APF is convex, then f is convex. Now, by the definition of epigraph, if you take 2 points x 1, then x 1 and x 2, then x 1 f x 1 and x 2 f x 2, both these points are in the epigraph, they belong to the epigraph of f. Both of these 2 points are in the epigraph, and you know that epigraph of f is given to be convex. So, which means that for all lambda you take between 0 and 1, for all lambda between 0 and 1, lambda x 1 plus 1 minus lambda x 2, lambda f x 1 plus 1 minus lambda f x 2 is in the APF. Again, by the definition of APF, it simply means that f of lambda x 1 plus 1 minus lambda x 2 is less than lambda times f x 1 plus 1 minus lambda times f x 2. So, in many cases, the modern definition of convex functions are given in this way, that a function is a convex function if the epigraph is a convex set. So, here here we go back to the usual definition of a convex function. I will just rub this to make it all right. Now, let me tell you about a text from which you would be able to know convexity or convex analysis at its best. So, I will refer to the most legendary and classical text in this area called convex analysis. This is published by Princeton, it was published by Princeton University Press in 1970 and it is republished in 1994 as Princeton Landmarks in Mathematics, and this is by one of the famous mathematicians in this area, Ralph Tyrrell Rockefeller, whose name is almost synonymous with convex analysis. So, anybody who is an optimization student, who is a graduate student in optimization, should have this book with him. And our own experience as a researchers, my own experience as a researcher in optimization, that even if I am stuck with some difficulty in convex analysis in my research, I just have to go to the book of Rockefeller, hang around with it for a few hours, and the answer would, I mean, you can actually figure out the answer. So, that is the power of this book. Now, let me tell you one thing, is that this book is not a book which has to be read from cover to cover. No mathematics books are actually, they are not story books that you read from cover to cover. You can follow if you read the places where you want, but this book specifically is not a cover to cover book as written by the author himself in the preface, that you really need to, this book is something which is to help you when you are in trouble, but this book is a must for all optimization researchers and graduate students in optimization. I would write here strongly recommended. Now, if you look into this book, I will just digress a bit. I understand that here I have a diverse audience, as I realized, rather I had said in the last lecture. Because of this diverse audience, I would like to reduce a bit the rigor that is required to do the mathematics of this subject. But however, to give the taste of what convex analysis is and or convexity is, we need to go and understand the idea of an extended value function. If you go and open this book Convex Analysis, in the very first chapters dealing with convex functions, you will see that Rockefeller speaks about convex functions which are defined from Rn to R bar, where R bar is R union the two infinities, minus infinity and plus infinity. It looks strange, but this is called the extended real line. Now, why you need to speak about extended real line? The reason is essentially as follows. You will realize as we go on that the unconstrained problems where there are no restrictions on the decision variables, such problems are much more easy to tackle than the problems which have restrictions on the decision variable, like we saw in the last lecture. So, how do I theoretically convert a problem which is a problem with restrictions on the variable to a problem which does not have restrictions in the variable? To do this, if you look at the problem that we are dealing with, minimize f x, x element of C, then this is a constraint problem. This has a restriction that x is pressed to C. Then consider this function which takes the value f x when x is in C and takes the value plus infinity when x is not in C. Though you might find it bit difficult in the beginning to appreciate this, but those who know some optimization have an exposure to undergraduate nonlinear optimization, they would realize possibly that this is what is called a penalization, that if you violate the constraint, I impose infinite penalty on you theoretically, and this is nothing but a theoretical model of the penalty function method, which is quite a common method in solving constraint optimization problems. So, this f naught, if f is convex, then this f naught is an extended convex function. But when you define extended convex functions, you have to have certain rules on infinity and minus infinity. So, we will not get into all this at this moment, we will come into the rules as and when required. So, when we will study convex functions and convex sets in details, which we will start from tomorrow, we will go into a bit of this issue, so that even if you get into these books like convex analysis or further books that I will say, you will be comfortable enough to handle these things. So, now let me get back straight into the modeling of this problem. Now, this problem which we will start referring to as CP, where f is a convex function and C is a convex set, is called an abstract version of a convex optimization problem, because though f has a representation, C does not have a representation. Sorry, this is a convex function and this is a convex set. Now, let me tell you a very simple thing, is that the set C in most applications is represented as a set of all inequalities usually. Where all these GIs are themselves convex functions. You might ask me, okay, what about, this is the standard thing, what about equalities? Equality constants are quite well known to you, possibly in calculus when you learn Lagrange multiplier rule, you would talk about equality constants. So, where is your equality constants? Okay, let me talk about a set C. So, I talk about this set C hat and that I talk about in R2, so that you visualize it, x y in R2 such that x square plus y square minus 1 is equal to 0. So, if you look at this, this is a convex function, and then if you try to sketch this set is nothing but this one, only the circle, nothing inside, only the circular ring. But then if you take a point here and take a point here and join it, except these 2 points, the whole line is outside the circular ring. So, this is not a convex one. So, if you put convex equalities here, you are not going to get in general a convex set. So, what happens, what sort of equalities you need to put in? The equality constraints that need to be put in to have a convex set at the end has to be of a particular form. They are of this particular form, they are called affine function. So, they are usually written in this form for a fixed given A. So, this is in Rn and this is in R. So, a linear function plus a translation. So, it is a translation of a linear function. So, basically a linear function, you see this is a linear function y equal to x, any linear function has to pass through 0 in R2 and then you just translate it down. So, this is or this or that, we can translate it up. So, this is an affine function. These affine functions need not be linear, but every linear function obviously is affine. Every affine function is a convex function, because you can just figure it out when you do not have to really do much work in figuring this out. Now, if you additionally define a set C, set of all x such that, of course, x is in Rn, I do not have to tell you that repeatedly. Gix is less than equal to 0 for all I from 1 to m, and Hjx is equal to 0 for all j from 1 to k, where this is convex and this is affine, then this set C is a convex set, and that is what we essentially want at the end of the day. Now, let me go back to straight to the optimization issue. What I want to show you now is that every local minima of the problem CP, that is the convex programming problem CP, convex programming. The term why I am calling it a program has a historical basis, but I will tell you that history later on. But let me just go in and do the math, that every local minimum is global. That is, there is no local minimum, every local minimum is a global minimum. So, if I take the problem CP and consider a local minimum x bar to be a local minimum, okay. If I consider x bar to be a local minimum, what I am supposed to do? Now, it means that there must exist a delta greater than 0 such that for every x which is in the ball centered at x bar of radius delta and whose points also lie in C, that is this set, the intersection of C and B delta x bar. For all such x's, f of x is bigger than f of x bar, right. Now, this is my convex set, and let this x bar is my global my local minimum. What I have showed that okay, there must be, by definition there must be a very bad drawing delta, and for any points in this intersection, this is a set C, for any points in this intersection f x is bigger than f x bar. This is the definition of a local minimum. Now, you take any arbitrary point y in this set C, take any arbitrary y. Now, join this y with x bar. Join with x bar. Now, if I am supposed to do so, if I am to join spelling does not look very nice, it is JOIN. Now, let me construct the line segment. So, any point on the line segment connecting y and x bar can be written as lambda y plus 1 minus lambda x bar, which means when lambda is 1 I have y, when lambda is 0 I have x bar. So, that means this is lambda equal to 1 and that is lambda equal to 0. So, when I am moving, dropping the value of lambda from 1 to 0, I am actually moving along this line segment. So, as I move along this line segment, I will come to this threshold point whose lambda is say lambda naught, which corresponds to z corresponding z naught corresponding to lambda naught y plus 1 minus lambda naught x bar. If I reduce the value of lambda from lambda naught, all the points lie in this line. So, what I can say is that there exists a lambda naught element of the interval 0 1 such that for all lambda between 0 and lambda naught, for them all z lambda, z defined by that lambda y plus 1 minus lambda x bar. So, now I am considering only those lambdas which are lying in this interval. This must be in B delta x bar intersection C. This is clear from the geometry here, from the picture here. Now, once I know this, what would I have? I have that f of z lambda is bigger than f of x bar. Now, which means f of x bar is less than f of z lambda, means f of lambda y plus 1 minus lambda x bar, but now this lambda is still lying between 0 and 1, and so by definition it is lambda f of y plus 1 minus lambda f of x bar. Now, if you do the manipulations, if f x bar cuts out from here, and because lambda is some quantity between 0 and 1 which excludes 0 and excludes 1. So, lambda is a positive quantity, I can divide both sides by lambda, because this f x bar would cancel off to give a 0 on this side. I would simply have this fact, it would imply that f of y is bigger than equal to f x bar. Now, you observe that y was just an arbitrary element, y was just an arbitrarily taken element in C, it need not be inside this, it could be anywhere else. So, for any arbitrary y, I have been able to prove that f of y is greater than equal to f of x bar. So, it is true for all y in C, thus proving that x bar is a local, not just a local minimum, it is a global minimum of the function f over the set C, and thus it shows that for a convex function every local minimum is global. And you must have observed that here we have not bothered about the differentiability of the convex function. We are not really caring whether this function is differentiable or not, and this fact is a very important fact, and you will see how important it is as we come on and as we proceed along and study more about convex optimization. So, we have just learned about the very important fact that for a convex problem every local minimum is global. So, this fact is very fundamental, and you will see how it helps us in the rest of the talk. But it is very important, as I have already mentioned, that this class of problems, convex optimization problems, have huge applications. Now, instead of going into specific applications, because that would be talking about domains which are not my domain, rather than basically if I am talking about say a problem in electrical engineering or problem in mechanical engineering, there are a lot of problems which can be modeled as the problem CP. Now, instead of that, let us look into some of the most important forms of convex optimization problems, and these are the classes which has played a major role in applications, because these are the classes of problems which appear repeatedly in applications. So, one of the most important class of problems is the one which is possibly known to many of the viewers viewing this talk, is the class of linear programming problems. In this class of problems, you seek to minimize a linear function. See, a linear function, you have only this part, you do not have the translation. Every linear function can be expressed as an inner product, which is a very simple fact from linear algebra, and I am just assuming that everybody knows what is the definition of a linear function. In case you do not, if you take any function from Rn to R, this function is said to be linear if these two properties hold. First is the property of additivity, that f of x plus y is same as f x plus f y, and the second property is homogeneity, that if I take any real number lambda and scale up this vector, scale up or scale down, and this is same as lambda f x, where lambda is in R. So, this is the definition of a linear function. Now, so you minimize this subject to linear constraints. Also, in most practical problems, there is a requirement that all the xi's are greater than or equal to 0. Now, of course, this is a convex optimization problem, because I can pose this as so here I have m inequality constraints and also some other group of inequality constraints, n inequality constraints, which I read as minus xi or x, whatever xj you want to put. So, the m plus n constraints. So, you can actually put this thing, put this aix minus bi, this whole thing into a matrix form, and you can write this as here. When I am writing less than or equal to 0, I am meaning that the component, every component of this vector is less than or equal to 0, and then I can also similarly write it like this, or you can equivalently write this as. So, what is this matrix A? This matrix A is a matrix whose rows are the vectors A1 transpose dot 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 AM transpose. This is actually the matrix A. Now, what you can do is you can actually add an additional slack variable, that is you can add an additional S and you can get a equality. So, the standard form of a linear programming problem is to minimize Cx subject to this is called the LP in standard form, and all linear programming books study this problem. We will have a scope to talk about this problem in detail more from a convex optimization perspective. Of course, this is a subclass of convex optimization. Now, the interesting part of this problem, you see all these are nothing but this is clubbing together of a class of affine functions, and this is of course minus each xi is a convex function, because minus xi itself is an affine function, linear function rather. So, this is, you see there are convex inequalities and affine equalities. So, this set is a feasible set is a convex set, the set C, which is in this case set of all x in Rn such that Ax equal to b and x is greater than equal to 0 component wise, then this set is a convex set. Now, this problem is interesting in the fact that this linear function has to be always minimized over a constant set. You cannot minimize it over just the whole of Rn. For example, if you take the whole real line R and you look at the constant function f x equal to x, this is a linear function, but it does not have a maximum nor has a minimum. So, it is unbounded on the whole real line unless you put say a constraint. Suppose you restrict the variables over this interval, then you know this is the minimum point, then you know this is the maximum point, this is a point where the minimum is achieved, this is a point where the maximum is achieved. So, the linear programming problem is essentially a convex problem, which is a constant problem. You have to have some restrictions like the set C. This problem, linear programming problem, was first studied during the World War time, and during that time it was the Air Force which had given certain problems to a team led by George Danzig in the US in the RAND Corporation, and they modeled those problems as linear programming problems, the type of problems that we had seen. So, Danzig was yet not sure what to call these problems, what name to be given to this problem. So, one day he was walking with the famous economist T.C. Koopmans, and then he said, okay, you know, all these problems have come out, they are all problems where you have to minimize linear functions under some linear or affine constraints. And Koopman said, you see, this is what you are doing, this is the program of the Air Force and you are trying to solve their problems, you are part of their program. So, why do not you just call them linear programming? So, it became, this term came to in vogue, linear programming, which had then translated into, in general, optimization in finite dimension is also known as mathematical programming, which lately is been now called mathematical optimization. So, another class of important class of convex optimization problems is a class of quadratic optimization problem under affine constraints, that is minimize Of course, A is again just before, like in the last one, this A you can easily understand this is an M cross N matrix. Usually when we study linear programming, it is taken to be a full rank, but that is really not necessary when you discuss the theory. So, A is again an M cross N matrix and B is obviously in Rm, which I do not have to tell you. Now, this problem is a quadratic problem. You see there is a quadratic form here, and this is the matrix defining the quadratic form. This function this part only, is a convex function, that is if you take just this part, then this is convex if Q is positive semi-definite. Positive semi-definite matrices are true generalizations of non-negative real numbers. That is, if Q satisfies this condition, then this is convex function. Now, if you take two convex functions f1 and f2 and if you add them, they remain to be a convex function. So, this is a convex function because this part is an affine function and you have added it to a convex function. So, this becomes convex. So, if you want to have a convex programming problem, then you have to assume that Q is positive semi-definite. PSD is the short form of a positive semi-definite used everywhere in the world. So, this problem is called a quadratic optimization, convex quadratic optimization problem under linear constraints. It is a very important class of problems because for example, in the sequential quadratic programming method, this problem is the class of sub problems that is solved, and this class of problems are repeatedly solved. So, trying to solve these problems is a very important thing to do. So, the above problem is called quadratic problem under affine constraints or linear constraints. Quadratic convex problem with affine constraints. Now, these problems were all studied in the 60s and early 70s, and convex optimization was, people were thinking that it was almost going to end. It was a time, 80s was a time for 80s and 90s was the time for the rise of non-convex optimization, with people talking about Lipschitz functions and trying to handle them. But they soon realized possibly that it is not so easy a game to handle non-convexity. Then came in the horizon a class of optimization problems which completely changed the face of optimization, and till date they remain to be a thriving area of research, and it has again brought back convex optimization to the central and core of, or rather into the heart of optimization theory and current optimization research. So, what I am going to now talk to you is a class of problems called semi-definite programming problems. On the face of it, when I write it down, it would look as if I have just copied the linear programming problem into a scenario where my decision variables are no longer vectors, but matrices. So, we will start by considering the space Sn of all n cross n symmetric matrices. Of course, you know a symmetric matrix is the one whose cross elements Aij is equal to Aj. Now, if you take the class of all square matrix, n cross n square matrix, if you stack up, if you take the first column and then stack up the second column below it, third column below the second column and so on, you stack up all the n columns. So, you will get a row, you will get a vector which is having n square components. So, which means every matrix, n cross n matrix, corresponds to some element in R n cross n. Now, this class where you have this matching between Aij and Aj is actually isomorphic not to R n cross n, but to a subspace of that which is R n into n plus 1 by 2. I will not take off the fun, I would let you try to figure this out. Now, S n plus is a set of all matrix A in S n. See, this is also finite dimensional space because it is isomorphic to this R n into n plus 1 by 2. This is actually the dimension of S n actually. So, A element of S n such that A is a positive semi definite matrix, is a PSD matrix. So, S n plus this set is the collection of positive semi definite matrices, right. So, if A is positive semi definite, it is often written like this. This is called the Loener ordering. Now, let me go back again to this linear programming part, right. Now, when I am writing x greater than 0, what is the set it is representing? It is the set of all x in R n such that all the corresponding components xi, each of the components is greater than or equal to 0. This set is called R n plus, and you might observe, because positive semi definite matrices are actually generalizing non negative real numbers, we have given the symbol S n plus quite in quite in harmony with R n plus. Now, once I know this, I am in a finite dimensional space, you might ask me what is the inner product between two symmetric matrices. So, if I take a symmetric matrix X, another symmetric matrix Y, what is the inner product between two symmetric matrices? This is trace of X transpose Y, but for a symmetric matrix X transpose is equal to X. So, this is equal to trace of X Y, right. Now, what I would now do, you will see I will write down a problem like this: minimize C x, where C is obviously in S n, and then take all the AIs in S n, and x is obviously in S n. So, all these AIs are in S n and I is obviously from 1 to m. So, I am just imitating the linear program, and x is either I write it like this, or in this Loener ordering form, just I have written x greater than 0. In the linear case, I have written like this. I can write it like this or this, whatever, same thing. So, this problem is called a semi definite programming problem, because ultimately the decision variable has to be a PSD matrix, semi definite programming problem. You might ask the question, oh, what a big deal, we have just changed the space from the space of vectors, we are in a space of matrices. It is just a linear programming problem in the space of matrix, but space of symmetric matrices, but the answer is no. In general, a semi definite programming problem is not a linear programming problem. Why it is not a linear programming problem is a question that we can only give when we learn something more about convex sets, that we will start doing tomorrow, and we will show that this is not a linear programming problem, but a convex programming problem in general. So, thus this class of problems cannot be handled by the methods of linear programming like simplex method, and a new set of methods has to be developed for them, and the semi definite programming problems are now showing great power in solving a class of problems called polynomial optimization problems, which are actually very difficult NP-hard non convex optimization problems, and they are showing great power in very far in order to solve such problems. These things are showing great power in order to get an approximate solution very fast. The power of these problems are very lately coming up, and they are coming up in many applications. There are commercial softwares now to solve this class of problems. So, it is very important for us that in this set of lectures in convex optimization, we will spend a little part with semi-definite programming problem. So, with this basic introduction about convex optimization, about the very basic facts about convex functions minimized over convex set, that every local minimum has to be global, and telling you some 3 important classes of convex optimization problem. First is the linear programming problem, second is the quadratic optimization problem with linear constraints, and third is a very important modern class of convex optimization problem, the semi-definite programming problem. So, if you want to know more about these classes of problems, I would suggest you a book called Lectures on Modern Convex Optimization. By Benthal and Nemirovsky. Sorry, so why? It is published by SIAM, Society for Industrial and Applied Mathematics. So, with this very basic introduction to convex optimization, that is what the title of the talk says today, what is convex optimization. I stop here, but let me tell you, this is a mathematician's point of view of lecturing. I have not given concrete examples. I cannot claim to be an expert in each and every different discipline, but if you look into these books, this book in particular, you will see there are a lot of important engineering applications in this book, which can be modeled as either linear problem or a quadratic problem or a semi-definite programming problem. So, thank you very much and good night.